Hello again, Sioux High Earth Science students. This is Mr. McLeod again with another amazing astronomy podcast. Today is part 2 of the life cycle of stars. We will specifically be looking at stars much more massive than our sun and what happens to them when they die. We will also be looking at their placement on what's called a Hertzsprung-Russell diagram and the age of the stars located there. So get your notes out, something to write with, and let's do this thing. Okay, before we look at the life cycle of stars larger than our sun, let's take another look at the HR diagram and talk about the age of stars. In the part 1 podcast, we talked about the temperature of stars. We said that blue stars are the hottest, while the red stars are the coolest. We also talked about our own sun's life cycle, and that as it ages, it will cool down because the hydrogen fuel in its core is being depleted. Now, take a look at the main sequence of stars on the HR diagram in this slide, and let's take some notes. Notice that most stars start on the main sequence here in the upper left. We're talking about right in this area right here. All stars start on the main sequence up here on the left. Write that in your notes. Also notice what color these stars are. They're blue. Based on what we know about the amount of hydrogen fuel in a star, this should make sense now. At the beginning of a star's life, it has the most hydrogen fuel it will ever have, and therefore will burn as hot as it ever will with thermal radiation. Write this down. As the hydrogen fuel burns off during its life, the amount of thermal radiation it gives off also decreases. Write that down. Now look at the color and temperature of the stars as they move down the main sequence. So as a star begins to live its life, it starts to move down the main sequence. And here I'm going to point to where our sun is. So you can clearly see our sun's not young. If it were young, it'd be up here in the left corner. We said it's lived out about half its life. If you look at where it is on this main sequence, that makes sense. Now, if we also look at the temperature of these stars as they move down this sequence, and the temperature is down here, we can also see that as they move left to right, their temperature decreases. If we follow our own sun, we can see that about right now our sun is, maybe 6,000 Kelvin is the temperature. As it ages and moves down this Hertzsprung-Russell diagram main sequence, it will get cooler and cooler. Even as a red giant, it will be cooler. And if we look at where our own sun is on the main sequence, we see it's now very yellow in color. In fact, we can see that it's yellow in the sky. We have also mentioned that the sun has lived out about half its life. And you can see that, again, based on its position on the main sequence. Remember, the sun will eventually move off the main sequence, but by cooling and becoming a red giant. So eventually it moves from down here up to here to become a red giant. But its temperature still going to remain cool compared with where it started. So what we can see is that the youngest stars on the main sequence are located in the upper left corner and the oldest in the bottom right corner. Write that down. However, when stars begin to die or burn their fuel out, They move first to the upper right corner as giants, where this arrow is right here, and then eventually move over and down here as they die. Write that in your notes as well. So eventually, these red giants will cast off their cooler outer atmospheres, and what's going to be left now is a core or a small little white dwarf, but it'll be hotter. It'll be much hotter. However, not nearly as bright. Remember, luminosity is brightness. So the sun is going to actually lose its brightness as it goes down the main sequence and lose its temperature. Then as a red giant, it's going to get brighter. And then as a white dwarf, it'll get hotter but dimmer. Write those in your notes as well. Okay, now let's look at the life cycle of stars much more massive than our sun. We will separate them into two categories and make a similar flowchart to the one we made for sun-like stars. First, let's look at huge stars. So we're looking now here on this diagram at huge stars. Now in your notes, write that a huge star is 1.5 to 3 times the mass of our sun. So get that down in your notes and start a new flowchart with huge stars at the beginning. Go ahead and do that right now. Recall that stars begin to die as their supply of hydrogen fuel burns up. This is no different with huge or giant stars. Now the difference is that huge stars cool down and become red supergiants. So you see here now they become a red supergiant, which makes sense. They're bigger than the sun. Right up here, our sun-like stars become red giants. But huge stars and giant stars both become red supergiants. Write that down in your notes and then fill it in your flowchart as well. Now, here's an important difference in the life cycle of massive stars. Remember that our sun becomes a red giant whose atmosphere explodes off up here. The atmosphere explodes off, and then it becomes a planetary nebula. Now, huge stars become red supergiants, like right here, and their atmosphere also explodes off. But because they're so much larger than our sun, their explosions become something important called a supernova explosion. A supernova explosion. So an explosion much larger than the one up here that forms a planetary nebula. Write that down in your notes. And also add supernova to your flowchart as well. Now I also want you to write that supernovas, and this is really important, are responsible for forming all the heavy elements in the universe. They're responsible for forming all the heavy elements in the universe. Light elements are formed in the core of stars. Heavy elements are formed from supernova explosions. We find those in the middle to the bottom of our periodic table. So write that down. Now, as the core of this huge star continues to collapse, and remember, it collapses because gravity's winning, because the fuel is running out, it eventually collapses into what we call, right here, a neutron star. Write that down, and now complete your huge star flowchart. Okay, finally, let's talk about giant stars. Now, in your notes, write that giant stars, and here they are in this diagram, giant stars. Write that giant stars are over 3 times the mass of our sun. Now, so you're going to write that explanation and also start a new flow chart with giant stars at the beginning. Now, you can see here that giant stars cool down because their fuel starts to burn out, and they also become red supergiants, just like huge stars do. So again, fill that in your flow chart. Now this big atmosphere also explodes off, and they form supernovas, just like our huge stars did. Add that to your flow chart. Now the big difference is with giant stars, they end up as what we call black holes. So again, write that down in your flow chart. So giant star, red supergiant, supernova, black hole. Now we'll talk more extensively about black holes later on in this class. Now it's also worth mentioning that black holes are often described as pure gravity. So get that down in your notes. They're described as pure gravity. And I want to explain to you why they're called pure gravity and why they're considered holes. Black holes form because the core of this giant star has now collapsed out of existence. It's completely folded in on itself, leaving literally a hole in space. That all there is left is gravity. I know that's very difficult to understand, but in a black hole is no more matter, just gravity. That's why light even gets bent down into a black hole, but mysteriously the only thing that comes out of it right now that we can see are X-rays. So write that down. I thought I'd end this part 2 with just some pictures now of supernovas. They're extremely important because they make heavy elements for us. Now here's a great picture of the birth of a neutron star and a supernova remnant. You can see now that we go from a red giant to a supernova explosion right here, and then what's left is this small neutron star. So the outer region of the star explodes, forms a supernova, and the supernova shines more brightly than an entire galaxy, but for only a few hours or days. So I'd like you to get that down, that supernovas shine more brightly than a galaxy, but only for a few hours or days. Most supernovas are extremely far away from us, so we don't really feel their effects. Now lastly are some pretty cool pictures of supernovas taken by the Hubble Space Telescope, and the pictures are provided courtesy of Harvard. So you can see a variety of colors, and you can only imagine that the colors might be based on the size of the star or how long ago the supernova happened. It would cool down after a while and go from blue to red maybe. But these things are fantastic astronomical events that we can now see courtesy of technology like our Hubble Space Telescope. Okay, done with part 2. Go to Moodle and grab those questions and answer them, and we'll get back to you soon. Thanks for listening. Mr. McLeod signing out.